Hello everyone, this is lecture 9, ECE350. Before I get to the lecture 9, which is impedance matching, I want to explain a little bit here, this circle over here. This circle is called standing wave ratio circle, standing wave ratio SWR circle. All right, what does it mean? If you have a standard wave ratio, S is basically 1 plus big gamma 1 minus big gamma, and big gamma magnitude is your reflection coefficient. As you know that your magnitude of the reflection coefficient doesn't change from load to all the way to any point of the line. Only thing changes is the angle, right? So if this is not changing, this should not change either. So if you take the radius as the reflection coefficient magnitude, and if you draw a circle, it's called standard wave ratio circle. That means if you go around this circle, over here, your radius, which is reflection coefficient magnitude, doesn't change, but your angle changing at different point. So that is the standard wave ratio circle. All right, and one other thing for this over here, one other thing over here is that when you get a point like this point over here is a load impedance right here, right, which is ZL. Obviously it's normalized value. If you go on the other side of the circle, which is 180 degree or lambda by 4, and you get the load admittance. And what is the admittance and impedance? They're opposite to each other right here. So what is the benefit of admittance in calculation? If you have a parallel circuit, for example, if you have parallel circuit over here, right? Let's say you have this is your Z1, this is your Z2. You're trying to find ZEQ, which is equivalent impedance, right? So ZEQ, 1 over Z is 1 over Z1 plus 1 over Z2, right? So in admittance, look at here, what's happening. So you just add them in impedance to find, in admittance to find equivalent admittance, you just add them. So that's the beauty of admittance, that in parallel circuit you just add them to find the equivalent admittance. Then you can inverse it to find the impedance. All right. So that was the thing I want to show you here before I get to the load matching. So let's go back to the load matching. Right here. So load matching. What is the load matching? So as you know that normally your transmission line characteristic impedance and load impedance does not match each other. So Z0 does not match ZL. But to minimize the reflection coefficient, if you minimize the reflection coefficient, you get more power transfer from source to load. That's the goal, right? So to do that, to match them, we add a matching network between the load at a point, let's say M prime over here, right? So this matching network needs to be designed. That's what is called matching network problem here. So we're gonna spend some time here to find out how to design the matching network. Okay. So what are the matching network look like? I'm gonna skip this one. Matching network could be a quarter wavelength transformer, or could be a lumped parameter like this, right? We're gonna concentrate on this lumped parameter for this chapter. So lump parameter, as I said, you have a load over here, right? Everything is admittance now because we're not using any impedance. Everything is admittance. So you have a load here. Then that load is not matched with Y0, right? To match it, we have to add something. So what are you gonna add? You're gonna add at a distance D, right? And that distance D is defined by a real part. Why is that? If you look at here, in the normalized admittance over here, Y in is basically you're adding YD at distance D from the load with your inserted matching network. So YS is the matching network. YD is the admittance of the load at distance D, right? If you add them, normalize, you use the smaller letter, add them. So GD is basically conductance, and JBD plus BS, right? So we're BS, we're only adding reactive part, we're not adding any real part, all right? So then this is the Y in, right? And if Y 0, which is normalized value of the admittance, it should be also just 1 plus J0, right? Because your loss transmission line does not have any what do you call it? Loss transmission line impedance is real part, right? So now you have to match this one with your Y in. So Y0 should be matching with Y in at this point here, at this point over here, right? So that should match each other. So match each other, that means your ZD over here should be equal to what? 1, right? So ZD needs to be 1. And your reactive part over here, this part should be equal to 0, right? If that part should be equal to 0, then BS become negative BD. Again, your GD and BD, those are the admittance, real part and reactive part at distance D from the load, at distance D from the load. So we're gonna walk from the load at a point where your real part is 1. Can you see that? So we're gonna walk from the load towards the generator where your real part is 1, okay? And at that point, we're gonna add a matching network to match with the line. So line impedance is Y0. Your combined admittance load plus your matching network is Y in, so that should be equal to each other. So how much we're going to work again from the load? We're going to work until we get the real part value 1. All right. All right. So that's one example over here. So we have this is your load. This is your Z0. So your Z0 is your 50 over here, and ZL is your 25 minus J50. We're gonna convert both of them into admittance, and we're gonna do all the calculation in admittance. Let's go to the next one here. So again, we're gonna make the normalized value right here, and we're gonna find the admittance. Admittance is basically this one is YL is basically 1 over ZL, right? So from here you can see that we have a GL value 0.4 and YL value is 0.8. Those are the real part and imaginary part, right? So now, as I said, this is a load. So let me draw the load over here. So I have a load over here. That is YL is 0.4 plus J 0.8. Then we're gonna add a what do you call it? Matching network at distance D from the load, right? Right. So again, we're gonna walk from the loads towards the generator until we get the real value is 1. So how do you know that? To find it, we need to have a real circle, right? So that's why your RL equal to 1 circle becomes ZL equal to 1 circle in the admittance environment. So this is the circle where the real value is always 1. So this is the real value circle here is always 1, and this is the circle over here. So this is your load ZL. This value is over here, and if you go on the other side, this is YL. That's the admittance value. So we're gonna draw the circle over here. So there's two circles. One circle is this is the load circle, and this is the real value 1 circle. When they intersect at a point right here, that is the point you have the real value is 1. Can you see that? So that's the value you have the real value is 1. So if you match the real value, then we can match the imaginary value too. At this point, we have the real value 1, and how much we have to travel to get the real value 1? So this is this point over here is my YL point. So I worked 0.063 lambda to find my first point where my real value is 1. So at this point, real value 1. So I have the YD1 at that point. So YD1 has two things. It has, why I'm saying YD1, because another point on this side over here also has the same real value 1. We're going to get to that next. So over here, YD1 has 2 points. You have GD1 plus J BD1, right? This is the one, it matched, so I have to match this one. So to match this one, you know that your BD equal to negative BS, right? Or other way around, right? So now that means your BS over here, that is the value of here, BS, right? The imaginary part of your matching network, BS, would be negative BD, right? So that means as soon as you know the BD over here, you know BS. So I can say for the first point, BS1 is negative BD1, right? So what that means, I have negative J158. That's the imaginary part of my matching network. Again, matching network, we don't use any real part for the matching network, only use the imaginary part for the matching network, because real part already matched with my load, on my transmission line characteristics admittance. All right. So this is my matching network imaginary part. Again, remember that this is my admittance, right? This is my admittance. So I have to find impedance for that. So let's go to the next one here. So now, again, you see that here, this is my admittance YS, which is actually BS. Then how to get from here to here, all right? So this is the admittance. I have to find normalized impedance. If you take inverse of that, you get that one over here. So that's my normalized impedance. Now I have to multiply by characteristic impedance, which is Z0, to find the actual impedance that is right here. So from here is j omega L, so it's XL is j omega L. So that's how you get omega. Your frequency is given, if you remember, your frequency is given, which is 100 megahertz here. You use the same frequency over here. If we use the frequency over here, so L would be 31645 over 2 pi f, and that will give you 50 nanohenry, right? So what it means over here, I have to add a 50 nanohenry inductor to get the matching. At what distance? At 0.063 lambda from the load. So at 0.063 lambda from the load, I have to add 50 nanohenry inductor to match it. That means at this point, at this, I'm going to take a different color here. At this point over here, your Y 0 equal to Y in, and Y in, again, Y in is a add of these two. Now let's try that. So Y0 is, remember, that is 1, right? 1 plus J 0. And Y in, now I have this over here. What is that? Y in, where did it go? Y in, okay, over here. So I have this for the Y in over here. So this is YD1. So this is Y in is equal to YS plus YD, right? So YS is 1J 1.58, right? Then YD is 1, that is negative here, right? That is negative. Let me do this again. So this is 1 plus J0. This is negative 1.58 J, then plus 1 plus J 1.58, right? So look at that. This becomes 0 here, and 1 equal to 1. So they perfectly match, right? That means there is no reflection coefficient. So you can do the same thing. You can do the same thing for this point over here at point D, right? Then you have to travel from here all the way to this here. This one here is like you're traveling from here to here. This length would be different. Let's see, it would be, you can calculate if you come from here to here, you can calculate that. Then you can do the same matching I just did for the last one. You will get the answer, and at this time you need your a capacitor if you do that at that point. All right. Okay, I'm gonna stop here, and I'm gonna get to the next video later.